Okay, so I think I have covered that for last activity, but I'm doing it for JKEE, another group. But if you are you from class JK50 or from another class from Dr. Mr. Zuhairi, they can always join. Okay, so this is what we're going to do today: time response. Okay, for that there are 4 things I'm going to cover with you today, which is an overview, refresh back our control, what we have learned in control. Okay, and then number 2 is the concept of poles, zeros, and system response. Number 3, I'm going to introduce you a first order system, and then also a first order system transfer function by testing. Only 4 things we are going to cover today. Okay, so for next tomorrow we're going to cover a second order system. All right. So okay, I have right in here. This one's supposed to be a blank. Okay. Okay, so generally, to review again, remember that I covered with you about the we have talked about 2 systems, which is elevator. If you still remember bangunan bistari elevator tingkat 10, okay. So we have talked about that system, and also we talked extensively a little bit about antenna azimuth position control system. Am I right? Okay. So these are the systems. So what we have covered so far, okay, we have learned how to make the mathematical model for the system, right? So what with mathematical model that we have learned is to make the transfer function. We have learned how to build the transfer function from a system. So what we are focusing on is just on the electrical circuit, but it's actually for actual system we're going to involve mechanical, electromechanical. Okay, so but we are not covered that in this subject. So another part is we learn how to develop the mathematical model and make it into state space equation. Okay, state space equation. Okay, so now for the next step is we're going to learn how to analyze the control system, the system. Based on our mathematical model that we get, okay, we need to analyze the model, okay. So there are 2 things that we are looking at when we analyze the model. Okay, the first one is we are analyzing the transient response. Okay, what is transient response? Remember, I like to give example about our lift. Okay, so there are 4 lifts, 4 elevators. Okay, so like I said, I like the elevators on the right, which is faster, okay, compared to the left, left of my side, which is a little bit sluggish. So those the conversation about fast, sluggish, those are actually in control. We are talking about the transient response. Okay, it's about transient response. And second is when we analyze, we need to look at the performance at steady state. Right? So there are 2 things that we are going to look at when we analyze the performance. Okay, so analysis tools, what are the tools that we're going to learn in this topic for today to analyze the performance, which is we are going to learn about the concept of poles, zeros, and system response. So what are these? Okay, so for this topic, chapter 4, we're going to learn about all these elements, analysis and analysis tools, and we're going to look deeply into first order system and then also a second order system. Okay, so these are the key elements in control engineering. All right, so first one, the poles, zeros, and system response. So for example, you have a transfer function, okay, Cs equals to 1 over S here. The numerator is S plus 2, over the denominator S plus 5. Okay, so okay, this one's supposed to be blank and you have to do it together. All right, so how is this in the block diagram? In a block diagram, it will be the input here is 1 over S. GS here, the transfer function is S plus 2 over S plus 5. Okay, so then we get CS here. All right. So this is the transfer function in the plot diagram. So how do we plot? What does it mean by poles and zeros? Okay. So the poles here, the zeros here are the numerator, which is -2. The symbol that we use for zeros is round. So this is the zeros for this transfer function for CS. Okay. So what is poles? Poles is the denominator. So in this case, the poles is -5. So the symbol for poles is cross. Okay. So the poles and zeros. Secondly, you need to know about the how we plot the pole and zero in the S-plane. Okay, so we have the S-plane here where it has the real parts and imaginary parts. So you just plot the poles -2 here, for example, and zeros is -5. Okay, why do we have to do this? It will give meanings as you progress to another chapter. Okay, so how is the system response? So this is, remember, this is in S domain, right? Okay. So when we remember, we use Laplace transform, okay, Laplace transform to transform it into time domain. Okay, so the time domain. So then from the time domain, we are able to get the system response. Okay, so for this case, the system response is you have an input here, 1 over S. So you know that there will be something, an input which is 1 over S, and you have some things, you have some output here. This is the system response, which is the output. Okay, so based on this concept, these are the 4 things that you need to know: the block diagram, the pole zero plot in S-plane, and also the system response. Okay, so next. Okay, so you can find this in the textbook. Again, this gives the more description about what is this here. Okay, so look at here, it has the transfer function S plus 2 over S plus 5, and you have an input 1 over S. So when it is plotted in the S plane, it goes like this. So what does this mean actually? Okay, so the input pole in the S plane, the input pole is actually located in the middle. You can see the input pole here. Okay, is here. Meanwhile, the system zeros is located here, S plus 2, and the system poles is -5. So from these tools, we can predict the kind of output response that we're going to get. Okay, so from these tools, you know that your CS will be, which is in this case, your CS will be RS times with your GS, the transfer function, which is 1 over S times with S plus 2 over S plus 5. All right, so it will be using partial fraction equation. Okay, you will get your CS is equals to A over S plus B over S plus 5. I hope you still remember. Okay, so from this partial fraction, so you get some constant value here, A and B. So then you can easily transform into a time domain, CT, which is A, a constant A here because it is S plus with B exponential minus 5t. Okay, so in case you lost, so this one, the conversion, we use table 2.1. Okay, Laplace transform. All right, so this is the general thing here. So this is what is presented here in the output time response. Okay, so in this case, in this output time response, we give the A value is 2 over 5 plus with the B 3 over 5. So what does this mean actually? The 2 over 5 here, which is a force response, which is the input that we give to the system. So in this case, it's due to this 1 over S step. Okay, the 3 over 5 exponential minus 5t is the natural response. And what happens to the system when it receives, it gets the input. Similar like elevator, we enter the elevator and we press button 10, so that is the input. So it's kind of a start input. So what happens? The elevator will move up and reach level 10. Okay, so that is a very straightforward, very simple example about the force response and natural response. Okay, any question?
No, ma'am.
Okay, so I'm going to proceed. Okay, example 4.1. Okay, given the system of figure 4.3, which is this figure. Okay, write the output CT, which is T in the time domain, okay, in general terms. Specify the force and natural parts of the solution. Okay, so what it says here is, first we multiply CS is equals to 1 over S times with S plus 3 over S plus 2, S plus 4, S plus 5. Okay, so it's actually, before this step, you will have 1 over S multiplied by S plus 3 over S plus 2, S plus 4, S plus 5. Okay, so what you're going to expect here, using a partial fractional equation, which have to be very strong in it. Okay, so you know that there will be one constant. There will be 4 constants. How do we know? Because we have 4 S here. Okay, so it will be K2 over S plus 2 plus K3 over S plus 4, okay, plus K4 over S plus 5. Okay, so this is how they get, this is how you get CS. Okay, sorry. Okay, so this one is the force response, which is due to the input. Input, that giving the input to force the system to go to the desired point that we want. Okay, so this is the natural response. Okay, so when we have it into this form, okay, then we transform it into, when we transform it into a time domain, which is we use table 2.1 to transform. Okay, then we will get K1, which is the force response, the amplitude of K1, and also the response of the combination of natural response in this case. Okay, so next, okay, now the skill assessment exercise 4.1 that you can try. Okay, so a system has a transfer function GS equals to 10 S plus 4, S plus 6 over S plus 1, S plus 7, S plus 8, S plus 10. So write by inspection the output CT in general terms if the input is the unit step. So how do we solve this? Okay, so you know that you have a block diagram, sorry. Okay, so it will be CS is equals to RS GS. And you know that your RS is a unit step. So unit step, it will be 1 over S times with 10 S plus 4, S plus 6 over S plus 1, S plus 7, S plus 8, S plus 10. Okay, so at the end, if you transform it, and you should expect that the kind of response that you get here will be in the form of a force response of A combined and plus with the natural response, which is the effect from this, which is the effect from 1, 2, 3, 4, 4 exponentials natural response. Okay. Okay. So next, now let's talk about first order system. Okay. So example of first order system. Okay. So this is one example of a first order system, which is A over S plus A. In a block diagram, it will be A over S plus A, and this is a unit step, which is an input here. Okay, so that's how it goes. Okay, so this system, okay, if we know that in terms of pose and zero in the S plane, in terms of pose and zeros in the S plane, you know that this is the zeros and this is the pose. So in this case, the pose is that it only have, the first order system only have poles. Okay, one pole. All right. So mathematically, when we want to transform the first order system from S domain to the time domain, okay, you're going to expect that you will have two kinds of response, which is the force response, EF, plus with the natural response, EP. Okay. So in this case, when you are using a partial fraction equations, you will get K1 over S plus K2 over S plus A. Okay, so K1 over S, in this case, it gives, for example, it gives 1, okay, minus K2 exponential minus AT. Okay, so this is how it gets to this point. All right, so let me analyze. Okay, what if we take T is equals to 1 over A? So what happens is that this equation will be 1 minus K2 exponential minus A times with 1 over A. So as it cross each other, you will get K2 minus negative 1, which is equals to 0.37. So this is how it gets to this point. Okay, so what does this mean? So CT is actually 1 minus 0.37. Sorry about that. This one is just K2, okay? So CT is actually 1 minus exponential minus AT, and if we have the time is equals to 1 over A, you will get 1 minus 0.37, which is 0.63. Okay, so when you talk about what is 0.63, when you talk about first order system, you have to, it is always synonym with 63%. 0.63 means that, okay, in a system response for a first order system, this is how the shape of the response that you're going to expect for the first order system. Okay, so 0.63 is 63%, which is 63% of final value at one time constant. This is what it means. So when we get 0.63 here, it means that the time that the system reached 63% of the final value. In this case, the final value is here, which is 1. Okay. Okay. So the time it reached 63% of the final value. So as it reaches here, 63% or 0.63, then this is the time constant. Okay. Okay. So what does this mean? Okay. So from the time constant, okay, you should be able to get the TR and TS. What is TR? TR is rise time. And what is TS? TS is cycling time. Okay, so 63% of the final value. Okay, when you get that, so you get 1 over A. So from 1 over A, then you get your A, your time constants, and when you get your A here, okay, 63%, you will get time equals to 1 over A. So from here, you get your A. So from your A, you should be able to get the rise time. You should be able to predict what is the rise time for this system, which is using this formula. And you should be able to predict what is the settling time for the system using this formula 4 over 8. So the key important things for a first order system is to find the time constant, which is A, which is, it is at 63% of final value. Okay? All right, next. Okay, let's look at the exercise first before we go to this part. Okay, here. A system has a transfer function GS equals to 50 over S plus 50. Find the time constant, setting time, and the rise time. So, you know that in general, a first order system, okay, the general form of a first order system the transfer function is equals to A over S plus A. Okay, so that is the general form. So you can see here, A over S plus A. Okay, so based on this transfer function, we can predict that we know that it is a first order system. So A here is the time constant. So the A here is the time constant. So from this, you should be able to find the setting time and also the rise time. Okay, so T is equals to 1 over A, right? So what do you get here? 1 over 50, you will get 0.02 second, which is the time constant is 0.02 seconds. Okay, so the setting time, Ts, is equals to 4 over A. 4 over A, which is equals to 4 divided by 50. Okay, and Tr is equals to 2.2 over A, which is 2.2 divided by 50. Let us check here first. Make sure that is right. Okay, so using these two formulas. So then you will get, then you should be able to predict that your Ts is equals to 0.08 second and your rise time is equals to 0.044 second. So when you have this kind of problems, okay, where it gives you the transfer functions and you know that the transfer functions is in the form of first order system, okay, so you can find the time constant, and then from the time constant you are able to find the setting time and also the rise time. Then you can predict the kind of output response. Okay, so the kind of output response here, you can to expect that it will go like a first order system. So it will reach a final value here. Okay, and there is some 63% here. At this 63% is where it's a time constant, which is here in this case is 0.02 seconds. So also the rise time is somewhere here at 0.04 seconds, 0.44 seconds. So this is the time, the rise time, and the setting time, the time it takes to settle is somewhere around here, 0.08 seconds. Ts and Tr. Okay. So example for an elevator system. For example, that elevator system 1. So we have 4 elevators here, right? 4 elevators. Okay. So the 4 elevators has different transfer functions. So this one will be, this one is G1S. Sorry. So this one is G1, G2, G3, and G4. So for example, that G1, the A, all elevators has the similar shape, similar type of transfer function, which is A over S plus A. So you know that it is a first order system. But for G1, for example, the A is equals to, let's make it like a table. Okay. So for G1, the A, G, and A. Right. Okay. So for G1, the A is equals to 50.5. For G2, A is equals to 50. For G3, A equals to 30. And for G4, A equals to 55. Okay. So from this, where you know that the transfer function is G over A S plus A, and the A is specified here for the 4 elevator. Okay, so based on the calculation, finding the time constants, and from the time constant for each system, you should be able to find the setting time and rise time for each system, and you should know mathematically, okay, which one has better performance. Okay, so while this exercise you can do it, okay, later on. So then we reach to the last part for today. Okay, so this is about all this while we learn about a system. We learn how to find the first order, in this case, okay, you are given the transfer function of the system. So from the transfer function, okay, you can find the time constants, and then you can find the setting time and rise time. It's a mathematical equation. The formula is given. Okay, but in actual system, for example, the antenna azimuth position control system, or in any other system, even the elevator system, it is not very straightforward. It is not easy to find the transfer function, to develop the transfer function. Okay, the system is already there, but okay, so to develop the transfer function where you have to do the single line tracing for the circuit is going to be a laborious job work. Okay, so the last part for today's lecture is how we should be able to work backward, which is if you are given a system, for example, an antenna azimuth, okay, so you know that this is the input, the desired input that we set, and this is the output. See out here, output to move that moves the antenna. So this output response of the antenna, okay, so the output response of for example, this is the output response of the antenna. Okay, so the shape of the response shows that it is like a first order system. This is an example. Okay, so in actual, you may not see antenna as a first order system because it has a very complex subsystem. Okay, so you know that, for example, this is antenna is like you use the multimeter, for example, a multimeter to measure the output here, to measure the output response, or maybe you use a DAQ card. Okay, you connect it to the laptop and it will give an output response like this. So from this output response, actually you can estimate the transfer function for this antenna position control system. Okay, how? Okay, so the first order, this is what we're going to cover here. So for example, in a general form of a first order system, it is CS equals to K over S plus A, which is if you separate these two, it will be K over A minus K over A S plus A. So in this form, this system, it gives the output transform is actually 2 over 5S of some constant here over S plus another constant over S plus 5. And we put it, when we transform it into time domain, it will be one amplitude plus with another amplitude with an exponential. This is what we have learned previous in the early lecture today, so which is combination of force response and response. So in this step, what you need to do if you are given an output response like this and you want to develop a transfer function, the first thing is the time constant. Remember that the definition of time constant is the time for the amplitude to reach 63% of its final value. So find the final value first. So in this case, the final value is 0.72. Okay, so from 0.72, okay, so you times with 63%, you get 0.45. So you find here the value of 0.45. At this 0.45, okay, so you down, then here you will get the time constant, which is in this case is 0.13. Okay, so at force response, okay, at force response here, which is actually is equals to K over A. So that means equals to 0.72 in this case. Okay, so how do we find K? K is equals to 0.72, which is the final value, times with 7.7, which is the time constant here, which is 1 over 0.13, Okay, so you will get the value of K 5.54. So from that, we can estimate that the transfer function for this system that produce this output is GS equals to 5.54 over S plus 7. Okay, so this is the block diagram of the transfer function. So GS 5.54 over S plus 7, S plus 7.7. So this is the kind of output response that we get. So you can work forward again. So from this value, okay, you can find the time constants, and then from the time constants, you can try to plot it here, okay, and then you can work on the rise time and also setting. Okay, so at the end of this, yeah, what we conclude from this lecture today is we talk about a system analysis of the system in the transient response only, which is in this, for today lecture, we are just covering the first order system, okay? So we are covering the first order system, which is we learn about how is the general form of the transfer function, which is GS equals to A over S plus A, okay? And from here, what we need to know for a first order system is the time constant, okay? So the definition of time constant is the time where the system reaches 63% of its final value, okay? So 63% of its final value, this is what you should have in mind, okay? So once we get the time constant at this point, you should be able to find two specifications for a first order system, which is the rise time and also the setting time. So the rise time and the setting time here is the transient response for the first order system. Okay, so for the next lecture, we're going to cover a second order system. Okay, that's all for the lecture today. Any questions?
No, ma'am.
No?
No, ma'am.
Okay,
No,
so
ma'am.
more clear? So I will put this one, I will put this in the, the e-learning later. All right.